Welcome to Workshop 7. Today we're going to be talking about vectors, and in engineering vectors are a very important concept. So there's two types of ways that we measure everything in the universe. We tend to either use scalar measurements or vector measurements. And let's try a couple of things. Let's try a thought experiment. If I said I ran 250 meters and let's say in 5 minutes, would you be impressed? And the answer is probably not. You'd be going 50 meters a minute. Ooh, he's doing, less than a meter a second. You would not be impressed by that at all. But what about if I were to add the words up the sky tower? So now we've got our big sky tower, flying saucer on top, pointy bit up there. I run up there 250 metres in 5 minutes. Now that would be quite impressive. Well, I think it would be quite impressive. There's a revolving restaurant in here somewhere. Okay, so what's the difference between me running 250 metres that way and 250 metres that way? There is a big difference. And the thing is, so what we say is velocity and displacement are a vector. So vectors, so a scalar is a number that just has an amount. And the classic one of those is temperature. That is the classic. Well, I suppose another classic one would be the number of apples you have, when you're at primary school and they say if you have one apple and you have 2 more apples, that's just pure scalar mathematics. But vectors have an amount, pardon, and direction. And the direction becomes important. Sometimes we can just use, sometimes when the direction isn't important, we can use the number as a scalar. Like speed. Speed is scalar. We just say we're doing 50 kilometres per hour. It however becomes a vector if I say going towards Auckland. So displacement is a classic thing. If I say I move at 2 metres, that's just distance. But if I say move at 2 metres that way, suddenly it becomes a vector. Velocity, or 250 metres up, is a vector. Acceleration, these are all classic vectors. Force, and so field theory, fields cause things to move in direction. But you also get lots of things which are not necessarily apparent as a vector, like area. And let's take one of my cue cards. Here's my cue card for this bit here. Does one of the cue cards look different if it's facing that way than if it's facing that way? So the question is area a vector? So does it look different that way than that way? If it does, then the direction that it's facing is important. And that means that, yes, area is a vector. And that becomes important when you're doing things like flux calculations or force calculations. So, so there's a couple of ways that we can represent a vector. We can represent a vector as an arrow with drawing. So the length is the magnitude, and the directions, whichever way we draw it, that's the direction. We can also, and we'll be covering this shortly, write 25 metres at an angle of 47 degrees. That's another way of writing a vector. It's got an amount and it's got a direction. Or we could draw it as a point on the XY graph and say that that vector is 3 along and 4 up from that point there. So you go along 3, up 4, and we can say that that's a vector. So those are common ways of representing vectors. We'll do a little bit more about those in a second. So in the old days, adding vectors. So if I have two forces, for example, well, the classic one is if I'm in a boat, if I'm a ship and I'm sailing along at, I don't know, 20 metres per second, and if there's a current going that way at 3 metres per second, or if there's a current that way at 3 metres per second, where am I actually going to end up? I mean, if I'm swinging along and there's a current going there, I'm going to actually end up going off at some angle. So in a case like this, my velocity, let's represent a vector with one of those. That's a very old-fashioned way of representing, well, that's a very classic way of representing a vector, and that thing's got a special name. It's called a twiddle. If you see that under there, it's a vector. Otherwise, ways of representing a vector are in bold, like the vector A, or to put a hat on it. So often you'll see things like unit vectors with a hat. So that's so. Okay, so back to my problem here. My velocity final is going to equal my velocity of the boat plus the velocity of the current. And these are all vectors. And you can't just add this together the old way. If it was scalar mathematics, I'd just go 20 plus 3 equals 23. Doesn't work that way in reality. So with vectors, we have to find ways of adding them. The easiest old-fashioned way of doing this is adding them graphically. So we'd draw an arrow, 20 metres. The old-fashioned way is to draw an arrow. Because it's 20 metres per second, you might make that 20 centimetres long, or 200 millimetres long. And then at the end of that, you add vectors nose to tail. I know Ian teaches this now, but just like dogs meeting each other, they go nose to tail. So there's my 20, and there I'll draw off my next vector, 3 metres per second. And if we're doing this old-fashioned way, I'd then grab a ruler, and I'd measure it, and I'd use a protractor, and I'd measure the angle. But I've set these up as right angle triangle, and we've been doing triangles now, so find the magnitude equals 20 squared plus 3 squared. Take the root of that. We use Pythagoras on that because I've set that up as a right angle triangle, so we don't have to use cosine rules. So 20 squared plus 3 squared, take the square root of that, equals 20.22 metres per second. You'll notice that's very different than if we just add those two numbers together in a scalar form. So what's the next thing we do? We find the angle. So in this case I know it's going to be tan. It's going to be tan inverse opposite over adjacent, that's TOA. So we go tan inverse 20 divided by 3 equals 81.46 degrees. And that's how they used to fly bombers around the place and aircraft around the place. That's how they used to get ships around the place, adding vectors like that on maps. But nowadays, so we can write this in polar coordinates as v total equals 20.22 metres per second, 81 angle 81.46 degrees. Or if we use rectangular coordinates, same example, the coordinate based off the coordinate 20 metres per second. Just out of interest, when we're using this system, we always, like a Cartesian coordinate system, we always start counting from there and go that way, so 90, 180, 270. Okay, so we always start there. Other ways that we use this, adding rectangular bits, I can say vector 1 is going to have 0x component, and it's going to go up 20 20y, that's 1. Vector 2, v1, v2, it's going to be 3 that way, so I can say that's 3x 0y. And the advantage of doing it in rectangular coordinates, of course, is you just add up all the x bits. You go 0 plus 3 is 3. And so we can say vector total, velocity total, equals 3, 20. And that is a full description of the vector by itself. If you want to later on, you can actually convert it into this form using exactly this method. This is a classic method because we can use it on all sorts of things. We can use it, we can use it on all sorts of things, and we can enter it into Excel, and this is how computer programs understand this a lot easier. Okay, what about subtracting vectors? Because subtracting, let's take that a velocity example. Change in velocity equals velocity final minus velocity initial, and these are all going to be vectors. And remember, if you've got the change in anything, you always take the final amount and you subtract the initial amount. That's for anything. So how would I do this? Well, there's my V1, V initial, my V final is that way. I take the V final and then I add the negative, there's my V final. And one of the things about V final minus V initial is equal to V final plus negative V initial. And what's the negative of V initial? Well, it's going to be the same size. So if this is VI, this is going to be negative VI. And we just stick that together, nose to tail, VI. And there's going to be our resultant. So that's going to be our final one that we can use triangles and things to work out. So subtracting vectors is very useful, especially for finding out changes and things like that. So this means that we can do basic addition, we can do basic subtraction for vectors. And yeah, so a lot of the time we'll break stuff up into Auckland. Like if I break stuff into vectors and add them all together. Like if I'm going to Auckland, I'll just add, I go Hamilton to Taupori. I go Taupori to, we still go Huntly, I believe, go up to Pokeno, and then I drive up to Auckland. And my trip is broken up into lots of little bits. I just add them together, nose to tail. Then I get a straight edge, and I just connect the first to the last. Done. So anyway, one of the useful tools that we'll be using, we can't go into detail here, but I have got a video of this on the engineering page when you get there. It's polygon of forces. If you add up all of the forces, hey, they're in equilibrium. If you're missing a force, you can work out what it is by bringing it back to zero. Anyway, that's later on. Okay, so we've got basic mathematics. If I've got two vectors, I can add them, I can subtract them. Can you multiply them? And the answer is yes. There's three ways. There's scalar, where you just make the arrow, if you multiply it by 2, a scalar number, you just make it twice as long. If you multiply it by 3, make it 3 times as long. There's going to be the dot product and the cross product. I'm going to leave Ian to teach that to you over this next week. And so those are our three basic forms of multiplication. And next thing is, can you divide vectors? And the answer is yes. The easiest way to divide a vector is to multiply by the inverse. Just like we do up here, with subtraction we add the negative, multiply the inverse. So this allows us with vectors to have all for basic operations. And so in this course, and usually we expect the engineers to be able to do a 3x3 vector or a 3x3, three-dimensional vector, but MATLAB will allow us to do much more complicated things. And if we're using a coordinate system, x, y, we can have many more dimensions. We can extend this. So vectors, really important to your engineering career. Make sure you get the hang of these. Most of the time you'll be doing these in computer programs and things and letting the computers do the number crunching. But you're still the one that says, oh, we need to use dot product or a cross product, or you're the one that still has to figure out what's happening. You're the brains of the operation, not the computer. Good luck.